Recording in progress.
Okay, hello everyone. Our speaker today is Michał Bobula from Borde University. He will talk about his work on quantum collapse.
So yeah, thank you for the introduction. The title is Mass versus long space in quantum gravitational collapse. Indeed, I will talk about the models of quantum gravitational collapse, and this talk is based on two papers. The first one I wrote with my PhD supervisor, Michał Bobula, and the first paper is devoted to the bands, and the other one is devoted to the long squeeze in the quantum gravitational collapse. So let me start with the reminder. You know, we all know this picture, but this picture does not prove that either black holes as they are defined in GR or even horizons actually exist. The reason for this is following. So these event horizons, teleological objects, are visible only for those who ever were and ever will be. So certainly not for us. So in other words, you have to have access to the entire past history of the universe and the entire future of the universe. And only then you can actually judge and say that the event horizon is there. So yeah, the existence of the event horizons is only known after the universe has ended. So what is the motivation for my talk? I'm looking for a consistent picture of black hole formation and evaporation, and also I look for observational signatures coming from these kind of models. So on the right, you can see the typical inconsistent picture of black hole evolution. This was already given by Hawking in his celebrated paper on the black hole evaporation. So what you can see, this is the formation of the Schwarzschild black hole and its subsequent evaporation. The resulting space-time clearly is not global hyperbolic. So there is a black hole information paradox. Clearly, we can know this just by looking at this conformal diagram. So in this talk, I look for the consistent picture. What I desire for the consistent picture. First of all, no singularities. This is quite reasonable expectations. The next one is no new fields or degrees of freedom, which are other than in the GR-like picture of black hole evolution. So no event horizons. This is quite counterintuitive. However, the absence of event horizons is the requirement that I believe that will give us a predictive theory, so that we will obtain the global hyperbolic spacetime describing the black hole formation and its subsequent evaporation. So yeah, here you can see the comparison. This is a typical inconsistent picture of black hole formation and evaporation. And on the right, you can see the black hole formation and evaporation according to Ashtekar-Boyobol paradigm. So there is no event horizon in the spacetime, only local trapping horizons is present in the spacetime. However, the exact fate of the collapsing matter as well as the trajectory of the local trapping horizon is local dependent. Model dependent. So, and this picture is a promise. It is promised because since there are no event horizons, we could probe or just detect signals coming from regions that are hidden from us beyond event horizons in classical theory. So let me show you one of the models which is compatible with the picture on the right. So this was given by Hayward in his paper on formation and evaporation of non-singular black holes. So Hayward considered the following static black hole metric with the following metric function. L is a parameter here. It is usually taken to be the Planck, M is the mass, X is the real radius. So this static black hole geometry has the causal structure similar to the Reissner-Roche spacetime, however, with the regular center. The black hole is regular. So clearly this spacetime is not globally hyperbolic. It has a Cauchy horizons, which are general unstable. However, if we consider a more complete picture of black hole formation and subsequent evaporation, we get this. This was given by Hayward in his in his paper. So there are three stages. This is the first stage, the black hole formation, the static stage, described exactly by this method, and the black hole evaporation. And the result is following. One obtains a globally hyperbolic spacetime with no black hole information paradox, no singularities, no event horizons. So yeah, in this picture, everything is predicted. Yeah, and this is a dream scenario for any effective quantum gravitational framework because it is a promise for the observational signature coming from the regions which are hidden from us beyond event horizons in classical theory. So in this talk, in the second part of this talk, I will talk about the detailed picture of the Hayward black hole formation. However, I will neglect the variation, the open predation. And just to mention as an aside, the idea that event horizons are just artifacts of GR was also supported by Hawking in his late paper. He wrote this explicitly that the absence of event horizons is a solution to the black hole information paradox, the only solution which is compatible with CPT preservation. So yeah, in the first part of my talk, I will consider the bounce model. So the bounce model was given in effective loop quantum gravity. This is non-homogeneous dust collapse model in this framework. The model was given by the Canadian group. So they reported very profound picture of the non-homogeneous dust collapse. So here you can see that the whole spacetime is very hyperbolic. There are no event horizons. Similarly, as in the picture of Hayward, there is a local trapping horizon bubble, and also as they claim, there are shockwaves occurring in this collapse model, namely there are space-time discontinuity appearing after the matter bounce. So what is the model? How this model is constructed? The model is about the applying of the tools of homogeneous isotropic loop quantum cosmology to this non-homogeneous system. How this is achieved? It is achieved with the discretization along radial direction. I will elaborate on this more in the next slide. So in this talk, I will answer the question, is it really the case for this model? Namely, what are the numerically computed conformal diagrams for this non-homogeneous dust collapse scenario within this model? So what is the model setup? First of all, what does it mean effective in frameworks of loop quantum gravity? So suppose we start with the classical GR, we perform loop quantization, we end up with loop quantum gravity, the quantum theory of gravity. And then, given a quantum theory, we can consider first like description, so-called effective dynamics. So in quantum theory, we construct suitable semi-classical states, and we calculate the expectation value of our operators with respect to these states. And at the end of the day, we end up with a deformed constraint algebra of gravity or quantum corrected trajectories within the classical space. These quantum corrected trajectories are these expectation values. So at the classical levels, before the quantization, spherical symmetry is imposed. We have a gravity coupled to the dust field. The background line in the following. We have a gauge effect fixation plane of Gaussian gauge and also area gauge that fix the metric components. So the next step is the loop quantization. Again, we aim to apply the tools from the homogeneous isotropic loop quantum cosmology to this non-homogeneous system. So one performs the discretization along the radial direction, and at each node of the discretization, one obtains the LQC like Hilbert space, and the overall dynamics is given by this Schrödinger-like equation. And the final step is the effective dynamics. One passes to the Eckernfest-like picture, and only after this, the continuum limit is employed. And effectively, one ends up with the one-first of the partial differential equations in the case of the marginally bound scenario. So what is the key observation for conformal diagrams? So double null coordinates, you say the pair U and V, has to satisfy the following conditions for the differential. And these conditions will give you some partial differential equations you have to solve. And we know that partial differential equations has to be solved with certain initial conditions, and what will be interesting that the given different initial conditions for these equations will determine the appearance of the conformal diagrams. I will explain it in a moment. So, okay, the main results concern the non-homogeneous, that's collapse, but let us first discuss the homogeneous case, namely Oppenheimer-Snyder collapse scenario. We have a constant energy density for certain interval, and the rest is the vacuum. This is valid for the initial time slice. Yeah, Oppenheimer-Snyder is the collapse of the homogeneous dust bowl. So, and here you can see the results for this case coming from the effective dynamics. On this plane, you can see the radial time-like geodesics in this space. And this is the initial slice. Here we have the areal radius versus a 5-parameter plane. So we can see that the surface, the dust bowl, is actually bouncing in this picture. Here you have the classical Oppenheimer-Snyder comparison. And also we can see that the time geodesics that starts outside the collapsing dust bowl, they penetrate the interior of the dust bowl and bounce at the spacetime region where the interior shells has already bounced before. So this is the conformal diagram for this Oppenheimer-Snyder collapse scenario. I think you have seen this diagram several times on this seminar also. So just for comparison, this is the classical Oppenheimer-Snyder case. The matter is bouncing and re-emerging in the new asymptotic region. So we have a presence of the Hayward horizon in this space-time. This is the initial size. And yeah, the exterior vacuum is described by this quantum corrected Schwarzschild element. So yeah, clearly the spacetime is not globally hyperbolic. What is interesting actually that this metric function is singular at the origin of the radial coordinate. This is actually manifest with the presence of the finite singularity, which occurs in the spacetime. The global structure is quite similar to the right-hand nostril. Yes, of course.
So on the previous slide, you have this crossing shaft. Yeah?
Yes.
So the big region is like this after this singularity is crossing this shockwave singularity. Yeah?
Oh, this is in homogeneous case. There are no shell crossing singularities.
So okay. So even in the but the big picture is homogeneous model. Or?
This is homogeneous model.
Yes, but on the previous slide was also homogeneous.
Yeah, this is homogeneous.
Okay, so there are different versions of homogeneous model. So this line or something different?
No, I think they are always the same. These are the geodesics that starts in the vacuum region at the initial time.
They're only geodesics. They're not dust particles.
Exactly. Yes. So they're like test particles. Let's say.
Okay.
So yeah, this is the conformal diagram. However, as I said, we can have different appearances of the conformal diagram. And for example, this diagram is was constructed for different initial conditions. I used to construct double null coordinates. However, it has exactly the same total structure as the diagram I had shown you before. So we can see how conformal diagrams are indeed flexible, so to speak. Okay, let me go to the main results, which are about the.
Excuse me,
yes?
I just would like to understand what about Hawking radiation?
In this picture, Hawking radiation was neglected. Like the back reaction of the Hawking radiation was
No, I'm just curious about the standard, forget back reaction.
Yes.
Just standard Hawking radiation.
Okay. So yeah, we can do this. We could
you do the calculation?
Yes.
Basically?
Yes. So we could do, okay, what does it mean Hawking radiation in this picture? We have effective spacetime, and we could do quantum field theory on that fixed effective.
That's what I mean.
Yes, exactly. And we could, yes, we can calculate the Hawking temperature at the event horizon here, which actually coincides with the local trapping horizon. So the Hawking temperature is just the surface gravity divided by some constant. Yeah.
So you can do explicit calculation just starting from vacuum at past infinity and obtaining the kind of a logarithmic transformation of
Yes.
In the future, right? I was in the standard case.
Yes, exactly. But I haven't done this. But in principle, yes, we can do this. Oh, there could be some subtleties because the non-geodesics, they cross the interior of the collapsing dust bowl. And this can affect the frequency change for the light rays that are penetrating the dust bowl in the calculation of the Hawking radiation, right?
Okay.
So yeah, let me go to the non-homogeneous dust collapse. So by some of us, it was discovered that in the non-homogeneous collapse, the so-called shell crossing singularities can be present. Shell crossing singularities are space-time points where the energy density blows up at a certain point, and also the Kretschmann scalar is also divergent. So here are the results for the non-homogeneous dust collapse. Again, we have a time-like geodesics from a real radius versus a fine parameter plane, and we can see where exactly the shell crossing singularities are produced. So they are produced in the region where the time-like geodesics that start for large radii are bouncing in the region where some of the other geodesics like this has already bounced before. So there is no surprise that there's high energy density in this region. Yes, here is the conformal diagram for the non-homogeneous dust collapse. It is, at the first glimpse, quite similar to the homogeneous case, as you can see. But there are critical differences. First of all, we have these shell crossing singularities, which are present here. So, and I believe that the dynamical equations are no longer reliable beyond the shell crossing singularities, and that's why I put the shadow on this diagram to mark this feature. This is the trajectory of the apparent horizons for local trapping horizon. Goes this way, goes back here, and terminates at this point. So what is important in this picture? That the future of non-infinity actually evolved into inner null horizon. And this has a very important consequence for this model. Namely, the event horizon exists for the non-homogeneous dust collapse. So there are no local equations that can determine the location of the event horizon. Only after I solved the whole dynamics, I could, and after I plotted this conformal diagram, only then I was able to say that the event horizon is actually present. So everything is numerically computed except for the event horizon. So yeah, there are no local equations that can determine its existence.
Okay.
Yeah.
So this inner null collection, so there is something beyond that, or is that?
This is quite squeezed, you know. Maybe I can do some other picture. Because on this diagram, the inner null horizon, it has the following shape, right? I don't know. And roughly speaking, yes, there is a region between the inner null horizon and local traffic horizon.
It's not defined in the horizon.
Oh yeah, this is the question I wanted to answer. We will discuss it in a moment. Yes, so this is exactly your question. So what's beyond the Cauchy horizon? So we try to explore the space-time beyond the Cauchy horizon. So we tested how the Schwarzschild-like metric element behaves on this geodesic in question with respect to affine parameter of geodesics. And we had found the following results. So that once we approach the Cauchy horizon, the function becomes very steep. So it suggests or indicates that the space-time could be not extendable, analytically extendable beyond the Cauchy horizon. So yeah, so the question whether the time-like singularity present, which is present in the homogeneous case, exists in the non-homogeneous case is still open. So yeah, we can see how different this diagram is from the original conjectured one. So the most important conclusion is that the event horizon is not present in this feature, contrary to the original findings. So yeah, now I will go to the second part of my talk. This is devoted to the long squeeze. So the idea is following. So suppose we have a homogeneous isotropic Oppenheimer-Snyder collapse scenario, and suppose that the exterior is a regular Hayward black hole. However, I will neglect the back reaction with the Hawking gradation. So the question is, what is the interior dust of the dust? Well, what is the interior homogeneous and isotropic FRW metric and its dynamics? So what is the Hayward black hole? This is, say, quantum corrected Schwarzschild metric. It has this correction marked with red, and the Schwarzschild versus Hayward, they are quite similar for large radii. However, at the origin of the radial coordinates, the metrics are very different. Hayward behaves effectively like a de Sitter. So, and based on this observation, there will be no surprise that in the to-be-derived cosmological dynamic, there will be de Sitter epoch. So yeah, the question is, what is the interior cosmological metric in the Oppenheimer-Snyder? And by the way, there are two descriptions that deliver Hayward black hole as a unique vacuum solution as spherical symmetry. These descriptions do not introduce new fields or degrees of freedom. The first one is defined only for space-time dimension d larger or equal to pi. This is so-called quasi-topological gravity. Can be regarded as an Einstein-Hilbert action supplemented with infinite number of higher curvature corrections. And the defining property of this theory is that the equations of motions remain on the second order in spherical symmetry. So yeah, this framework gives the Hayward as a unique vacuum solution, spherical symmetry. The other description is what developed by Vilenkin group. This is the framework of polymerized LTD space-times. So starting from Hayward black hole, we can reconstruct specific polymerization or deformation of our gravitational Hamiltonian so that the Hayward black hole is a unique vacuum solution. But this framework requires fine-tuning. We could start with arbitrary static black hole and then reconstruct the corresponding polymerization. So yeah, what are the assumptions of the model? So the Hayward is in the exterior, and there are also the following: that the Israel-Bernoulli junction conditions hold at the boundary, the surface of the collapsing dust ball, and also there is a conservation of dust energy momentum tensor. And these assumptions fully determine the dynamics of the interior of the dust ball. So I end up with the following modified Friedman equation. And there are two families of solutions that expanding and contracting. In the collapse, I think I choose contracting solutions. So we have the following plots, K factor versus proper time of moving observers. So we can see that the universe is contracted for the small values of scale factor, it enters the de Sitter like epoch. So the collapsing matter is being decelerated. the scale factor is equal to 0, is only approaching the asymptotic limit where t goes to infinity. We can expand this expression. Here we can see the following, that this is the classical path coming from GR, plus infinite power of higher order corrections, which are weighted by consecutive powers of the time. What is interesting, suppose we truncate this power at the second order, and we effectively get loop quantum cosmology, namely the bouncing dynamics after the truncation at the second order. So there are no curvature singularities, even when the scale factor goes to 0. So the universe is then like geodesically complete. So this is slow roll without slow roll, because in these dynamical equations we don't have a flattened field. We have a graceful entrance to this quasi de Sitter like inflation. We can purely geometrically we can compute the slow roll parameters and indeed confirm that this is this kind of inflation. Energy density is the version of the final collapsing. And yes, here we can see the conformal diagram for this modified Oppenheimer-Snyder. We have a following picture which is much richer than the one coming from the classical theory. The collapsing matter is decelerated, and the collapse terminates at this point, and this is important, that this is the point on the conformal diagram, after infinite time as measured by the co-moving observers. So yeah, we have a long squeeze instead of the classical big crunch or bounce. Yeah, the space-time is geodesically complete. So we learned that in the collapse setting, the mechanism, which is similar to the cosmic inflation, actually decelerates the collapsing matter and prevents it from the singularity formation. We have also the following lesson for cosmology, because we learned how cosmologists can circumvent so-called Borde Vilenkin Guth theorem. This theorem states that the inflationary spacetimes are passing complete. So this theorem applies for the cosmologies where the expansion or contraction is monotonic, so no bounces allowed. And this cosmology, for instance, I derive for a universe of infinite size is singular, according to the Borde Vilenkin Guth theorem. However, if we consider a finite region, finite sector which is homogeneous and isotropic, with non-homogeneous vacuum on the outside, then the overall spacetime can be geodesic complete. So this is how the cosmologists, let's say, can circumvent the Borde Vilenkin Guth theorem. If this is unclear, please ask me a question right now. Yes, so, and this is the comparison with the result of Hayward. Hayward considered the formation of his black hole from collapse of the null fluid. Here I consider the collapse of the dust ball. I neglected the final stage, which is the back reaction with the Hawking gradation. However, still we can see that the first two stages, namely the black hole formation, like this region, and the static phase, are compatible with each other. The trajectories of the trapping horizons are compatible with each other at these two stages. What is important in this diagram? That the collapsing matter does not cross the Cauchy horizon. It means that there is a chance, because infinite time is enough time for a black hole to completely evaporate this before, so that the matter is not crossing the Cauchy horizon.
You don't know that because you don't know about the back reaction, right?
Exactly. Yes. So this is just a speculation, what I'm saying. And yeah, yet another diagram here. This is another speculation. Yes?
So in the previous diagram, there was Cauchy horizon.
Yes.
So now you have Cauchy.
Yes, yes, indeed. This horizon is the Cauchy horizon. However, this is okay, this is a speculation. However, this is what I expect what would happen if we include the back reaction of the Hawking gradation. So the collapsing matter is not crossing this line, so there's enough time so that the Hawking radiation could completely evaporate the black hole, so that this horizon will be time-like again, and these segments will reunite, so that the overall diagram will be compatible with the one given by Hayward. So this is one scenario. The other one is this one, like it takes infinite time for a black hole to evaporate. Okay, so let me conclude. So the first part was about the bands. It was non-homogeneous dust collapse in effective quantum gravity. I concluded that the shell crossing singularities, they exclude the large regional spacetime from its reliability, because we shouldn't trust the dynamical equation beyond the shell crossing singularities. And the most important conclusion is that the collapse cannot take place within single asymptotic region. So we do not get a globally hyperbolic spacetime in that picture. We have an even horizon, which is highly illogical object. So what is beyond the Cauchy horizon is still remains the open problem for this model. I also presented the model concerning the long squeeze. This was Oppenheimer standard collapse into a Hayward black hole. So the resulting spacetime was geodesically complete. There were no singularities, however, there was an even horizon present in this spacetime. So we got a slow law without throw law. So no inflation field, no new degrees of freedom. This picture, we learned that the cosmic inflation in the collapse setting is the mechanism that prevents the black hole singularity formation. There are similarities with the model inspired by asymptotic safety. The models are quite similar. However, the one obtained within asymptotic safety is actually singular at the final collapsing point, whether this one is not. And in asymptotic safety, you have a rank gravitational Newton G constant. So you have a nice interpretation. What is inflation? The inflation is the stage in evolution where the gravity is quite weak, much weaker than according to GR. Yeah, this is so-called anti-stream mechanism. So yeah, and from this model we learn how inflationary spacetime can circumvent the Borde Vilenkin Guth theorem. So what is the outlook? So the Cauchy horizons instabilities, it takes several models which are based or inspired by the low quantum gravity, string theory, or asymptotic safety. I have never seen a model which will be successful both in cosmology and black holes without implying the existence of the Cauchy horizons. However, from the paper of Hayward, we learned that the back reaction with Hawking radiation can solve the problem, because in the diagram given by Hayward, there were no Cauchy horizons in the complete evolution of the black hole. So how to solve the problem? We need to make apparent horizon time like again. So we have to prevent apparent horizon from remaining now. We have to make it time-like again, so that these local trapping horizons reunite, so that the no event horizons will be formed or Cauchy horizon. So I think that the global hyperbolicity can only achieve with the back reaction. So this drives me towards a suggestion or idea that the back reaction could be a necessary ingredient for predictive effective quantum gravitational effect. Okay, this idea comes from the considerations in spherical symmetry. However, will the problem be different, or much different outside this very spherical symmetry? I don't know, but I would doubt. And finally, I think we can write a cosmological puzzle with black holes. I think that the evaporating regular black holes are good candidates for the dark matter constituents, because the evaporation time from rough estimates can be infinite, so the time for the evaporation could be much longer than for the Schwarzschild black hole, and for Schwarzschild black hole the constraint, the observational constraint are excluding this this possibility. And finally, you can ask the questions: is our universe geodesically complete in the light of this observation on Borde Vilenkin theorem? So yeah, thank you for your attention.
Yes.
Maybe I share.
Yes.
You said that the Hawking radiation will probably solve the problem. It's non-predictable space.
Yes.
But is it not a bit strange because Hawking radiations are related, let's say, so the strict derivation is for the spacetime that have the infinite, so they have this event varieties. Yes? So something that comes
Exactly.
to the
Exactly.
scrap.
Yes.
So whether it makes sense at all to say about Hawking radiation, the spacetime that does not have varieties.
Yeah, exactly. Thank you for this question. So Hawking radiation was derived for the Schwarzschild black hole, but note that for the Schwarzschild black hole, the event horizon actually coincides with the local trapping horizon or apparent horizon. So I think that what is relevant for the Hawking radiation is actually the presence of the local trapping horizon. So in the Hawking calculations of okay, these objects coincide. However, what is important in the picture of the black hole evaporations, because in the Hawking calculation you trace back the light rays that reach the square plus to square minus, and yes. So and what is important is how the frequencies change for these light rays, and such a frequency change can also be present in spacetime without event horizons. So I expect a similar thing happening for the spacetime as well that do not possess event horizons, because what is actually important is the frequency change. And also, even in literature, you have models like the moving mirrors models in Minkowski spacetime. So in this model, there's a moving mirror that reflects the light, which is coming from square minus to square plus. There's a frequency change, and in these models you can mimic the Hawking radiation with very good precision as well.
Well, I'm not convinced, because in my understanding of the essential point of Hawking calculation is the existence of an unpredictable global transformation.
Yes.
Of course, the redshift or the, I don't know, blue shift effect is relevant, but what's essential is that you have really the Hilbert space of scribe plus, and the Hilbert space of scribe minus are not identical. They're just related they are related by non-trivial transformation.
Yes.
And so that's why you actually trace it back, and then you see that not everything, not all the signals coming from the past actually can reach you observe a future infinity. And I think this is the basic ingredient that you need to have a thermal Hawking radiation.
Yes, so I agree. The non-zero coefficients of Borde transformations are indeed required for the presence of the Hawking radiation. However, these non-zero coefficients will be present, can be non-zero for spacetime without event horizon.
No, that's true, because you have also creation of particles in it's not right. But I think it's this computation of Hawking, because this rate
So,
really related to the fact that you have a need, and it's well approximating.
Yes.
Let's say the Borde coefficient, only because you have the event horizon.
Yes.
But in those topological setup, you have a time-dependent matrix, and that's the reason why you have future Borde transformation. Here, the space-time is static.
No, it's neither.
So
Well, the outside.
here, for this speculation, the metric is not static.
Okay.
Exactly like in the picture of the Hayward. So we have a radiation coming out. And
Then of course, Okay, good. Do you
I have a question.
Yes.
Sure.
You see, your first slide, you showed the picture taken by the event horizon telescopes.
Exactly.
All this consortium. Okay.
Yes.
Very beautiful, very nice, and of course I agree with you that looking at this picture is very difficult to say that there is an event horizon. Fortunately, during the last 10 years, we are observing black holes also in a very extreme, unusual state when two black holes merge.
Exactly.
How your picture of the gravitational collapse and the outside of a black hole will influence the process of merging of the black holes.
Oh yeah, so everything is about the precision of measurements, because, for instance, what people expect, they expect that the time that has passed from this point to this point, like the complete black hole, the horizon formation, and this disappearance could be of the order of the age of the universe. So, for example, if we take picture of this kind of object, I expect that we will not see many differences with the model coming from general relativity if we compare these two descriptions. So when it comes to the black hole measures, at this point I don't know. So everything is in spherical symmetry. The black hole measures are outside spherical, formulated outside spherical symmetry. So at this point, I don't know what would be the exact difference or relevant difference.
Well, but you see, since the accuracy of the measurements of the black hole mergers is increasing, and it will increase further, students too, and it will be, I think, very interesting to find out if your picture of the process of gravitational collapse leads to some measurable, observable effects.
Yes, I completely agree. So yeah, I thank you for this comment. But at this point, I think I cannot add anything more.
Okay.
Yeah, could you, just following this question, could you tell me for the astrophysical black hole, this additional, this addition in denominator, what is the size of it
So
roughly?
this,
Yeah.
people usually take it as the Planck.
Yes,
Okay,
yeah, I agree.
These are the Planck units. However, I keep L explicit.
Yeah.
So I'm taking this as a Planck length, but I do not have to. So this is a parameter here.
Yeah, no, but what I wonder, what is the size, what is the number for astrophysical black hole? It's going to be very small, right?
Yes, absolutely. To give you precise number right now, I can't do this.
Okay. So it's gonna be, all right, anyway, so this solves the problem because the correction to the position of the horizon for a physical black hole should be by many orders of magnitude smaller than what we see.
Yes, and also in this picture, this could be visible that for large radia, these metric functions coincide very quickly.
Okay, any more questions? If not, then have the speakers. Okay, I will have a